Hello, welcome to the Crazy Hat Chemist. Today we're doing the 11th video on gases in a series of 16. Today we're going to be doing the ideal gas law. So let's get moving. So the ideal gas law. Here is the ideal gas law. It's PV equals nRT. That's Pivnert. So P is for pressure, V is for volume, N is for the amount of gas, R is the gas constant, and T is the temperature. I mentioned that gas constant, and that is, there are many different values for the gas constant. I'm just going to show you two here today. So the first one is 0.0821, that has units of liters atmospheres per mole Kelvin. The second one is 8.314 joules per mole Kelvin. If you look in the upper left-hand corner there, you should see a bunch of toys, a bunch of blocks and stuff like that. I don't know if you remember when you were a kid, you had this round circular object with a bunch of different shaped holes in it. And then you had some blocks that were different shaped. You had to find the block that fit with the shape in the hole of the circular object. And so like the star fit in the star hole, the square fit in the square hole, the circle fit in the circle hole, the triangle fit in the triangle hole. And that is related to the units for the gas constant. So if you look at the units for the gas constant in the left-hand gas constant with the number that's associated with 0.821, it has units for volume is liters, units for pressure is atmospheres, units for the amount of gas is moles, units for temperature is Kelvin. So make sure that those are the units that you need to plug into for the gas constant. And those are the units for all the other values, for the pressure, the volume, the amount of gas, and the temperature. Make sure you pay attention to that. The density equation derived from the ideal gas law using molar mass. P is for pressure, M is for molar mass, RT, that's the R is the gas constant, and T is the temperature. The ideal gas law mathematically works very well at low pressures and high temperatures. That is, low pressures and high temperatures, the ideal gas equation using the math will be very close to what it actually is. Now, I hope you do think about this, and that is, this equation only works with gases. It doesn't work with liquids, it doesn't work with solids, it doesn't work with things in solutions. So here's a derivation of the ideal gas law. We've already talked about Boyle's, Charles, and Avogadro's law. So if you look at all of these laws here, and there are relationships, volume is proportional to 1 over pressure in Boyle's law. Charles' law, its volume is proportional to temperature. Avogadro's law is volume is proportional to the amount. So if we combine these three gas laws combined together, and we maintain the volume on the left-hand side, 1 over pressure on the right, temperature on the right, N on the right, then we get the following. You should see that that is highly correlated to the Boyle's, Charles, and Avogadro's law there. Now we're going to have a multiplying factor here to make sure that the units actually work, and that is a proportionality constant. The next thing we're going to do is we're going to make sure that this is all in one line with no denominator term. So we're going to get rid of that P, that pressure term in the denominator. So we're going to multiply both sides by P. And then we get PV equals nRT. That is the ideal gas law. The ideal gas law has R as a constant. We already talked about on the previous slide. And I also mentioned on the previous slide that this ideal gas law mathematically is a good approximation. So make sure you look at that temperature pressure issue. It's a good approximation. And it's a good approximation under the following conditions. Number 1, the molecules of an ideal gas do not interact with one another. That is, there are no intermolecular forces. And number 2, the combined volume of the molecules is much smaller than the volume that the gas occupies. That means that the molecules take up little to no space compared to the volume of the container. All right. Let's do two calculations here. Today, the first one is number 7. What pressure in torr will be exerted by 350 mils of a 0.0052 grams of methane gas at 17 degrees Celsius? So here's the ideal gas equation right there, PV equals nRT. We're solving for pressure, so we're going to divide both sides by volume. Here's a little rearrangement. I just did that right there. The next thing that we're going to do is we're going to plug in the ideal gas constant as is appropriate here. So that's right here. So what I've done is I've plugged in the ideal gas constant, and that is the 0.0821 with the appropriate units that's associated with that gas constant, liters, atmospheres, moles, Kelvin. That will let me know that the amount of gas, that is N, must be in moles. The T, that is the temperature, must be in Kelvin, and the V, volume, must be in liters. So I need to rearrange all the numbers that I have in the problem that are given into those particular units. We're going to start off with N, and we're going to solve for the number of moles. We have grams, and we're going to convert that to moles using the molar mass. Look at your stoichiometry unit if you want a review on that one. But here it is, the 0.0052 grams of methane. That actually has 3 leading zeros. The leading zeros do not count, and it has 2 significant figures in the 0.0052. Okay, and then I'm dividing by the molar mass. That gives me 3.2 times 10 to the negative 4 moles of methane. That actually still has 2 significant figures. The next one we're going to do is a conversion of temperature. It's 17 plus the 273.15. The 7 in the 17 is in the ones column, and that has, in the ones column, it needs to be significant. That's why there's a decimal after the 290. Because that zero, that trailing zero, must be significant, therefore I must add a decimal, and that's in Kelvin. The next thing we're going to do is we're going to convert that 350 milliliters into liters, and here that is. We're going to divide by 1,000, and we still maintain the number of significant figures in the 350.0 milliliters. That's 4 significant figures, and there's 4 significant figures in 0.3500 liters. That is the 0 point. That first zero is a leading zero. Leading zeros never count. But the trailing zeros after the 5 are trailing a non-zero integer, and there's a decimal in the number, so they do count. Now what we're going to do is we're going to plug all this into the pressure equals nRT over V. So I've plugged all those in. Hopefully you see that the units will cancel out. The moles will cancel out, the liters will cancel out, the kelvins will cancel out, and I'm left with atmospheres. I'm solving for a pressure, so that's a good thing. I'm going to look at the number of significant figures, and the least number of significant figures that I have on any number in this problem is 2. So my answer will have 2 significant figures. I'm going to solve this, and I have 2 significant figures. That's 0.022 atmospheres. The 0.0, those are not significant because they're leading zeros, and the 2, those 2 count because they're non-zero integers. Now I'm going to read the question again, and it says, what pressure in torr? I just solved for the pressure in atmosphere, so I'm going to convert these atmospheres using the unit conversion to go from atmospheres to torr, and then I'm going to solve this, and that will give me 2 significant figures, but in the correct units that the question is asking for, and that's torr. So it's 17 torr of CH4, that's methane. All right, let's do the next problem. Here we go. Bam. Gas calculation number 8. How many grams of nitrogen gas are at the following conditions? 20 degrees Celsius, 76.5 kilopascals, and 150 milliliters. So I've rearranged the ideal gas law this time already for you, and I solve for N. That's the amount of gas. So N is equal to PV over RT. And just like what we did in the previous problem, we're going to substitute what R is with the correct number and units. And that's what I've done right here. And that lets me know that my pressure needs to be in atmospheres because the units for the gas constant are in atmospheres. The volume units need to be in liters, just like it is in the gas constant, and the temperature units need to be in Kelvin, just like the gas constant has. So I need to convert my pressure, the 76.5 kilopascals, into atmospheres. So let's do that first. So 76.5 kilopascals. And I'm going to multiply and divide by that unit conversion, that is times 1 atmosphere, divide by the 101.325 kilopascals, and I got the same number of significant figures that I had in the original pressure. That is 3 significant figures, and that answer is 0.755 atmospheres. Now I'm going to convert that volume in milliliters into liters. So here we go on that. That's 150 milliliters. That has 2 significant figures. That trailing 0 in the 150 doesn't count because there's no decimal in the number. And I'm going to divide by 1,000. That 1,000 has an infinite number of significant figures, just like the 1 in the 1 liter has an infinite number of significant figures. I got 0.15 liters. Now I'm going to convert my temperature. I'm going to add 273.15. It's 20.0 is the original number. It has 1 decimal place, and that is in the 10th position, so that's why it's rounded in the 10th position at 293.2. The 0.2 is in the 10th position. Now I'm going to plug this all back into that equation that I had previously there And here we go. Those numbers are all there. I'm going to look at the number of significant figures. I'm going to look at the units, make sure the units cancel out. That is, the atmospheres cancel out. The liters cancel out. The kelvins cancel out. And then I'm going to have 1 over moles in the denominator. So I'm going to flip that and I will have moles. So I have 2 significant figures in this answer because it has the least number of significant figures of the numbers that I plugged into this equation. So that's 4.7 times 10 to the negative 3 moles of nitrogen gas. And this brings up a point. I'm hoping that you remembered your diatomics. And nitrogen is a diatomic. So that's why it's N2. I'm going to reread the question again, and it says how many grams of nitrogen gas are in the following? And it's how many grams? I just solved for moles. So now I need to convert these moles into grams using the molar mass. So here's my molar mass conversion, and that's why I really needed to know that that was a diatomic, that nitrogen was. I'm going to have 2 significant figures in my final answer, and here's my final answer, and it's 0.13 grams of nitrogen. Hopefully that makes sense for you. That was a hard problem, but really good. All right, folks, so that was the 11th video in the series of 16 on ideal gas laws. The next one is why STP? Who cares? I do. You will too. I'll see you later. Have a good day.